This is the application of multivariable calculus in the engineering portion of my project. So the occupation that I chose for this project is the same as the one before, which is civil engineering. This is because I plan on going into the field and there are endless possibilities of applications of multivariable calculus in problem solving within the career. There are many presented problems that engineers have to solve on a regular basis that require multivariable calculus and the problem-solving steps used with the class. The most prominent of which are problems with deciding the appropriate scale for projects within their environments, as well as deciding the process by which they will be constructed. For this assignment, I would like to focus on the problem of designing and constructing arch bridges, which are one of the most simplistic types of bridges to build. In order to solve this problem, there are multiple steps involved. First, the engineers must decide on the scale, and this can be done using much of what we know with curves and shapes using polar coordinates to create an arch over the necessary area. Then, they will begin to create an understanding of the bridge's surface, which can be found using double integrals. This step also requires knowledge of the volume of the bridge, since arch bridges are solid structures unlike any other bridge style. This would require them finding the necessary volume using more integrals of the curves and the flat surfaces of the build. Lastly, the construction begins, and this requires a deep understanding of angles and force vectors to build a sturdy structure. We covered force vectors early in the class, and it involves a lot of physics as well, but force vectors are incredibly important with arch bridges since they are built directly into the foundation that they sit on, and they need to be sturdy enough that whatever is passing on top of it doesn't cause it to cave in. The most important thing about civil engineering is that the purpose of it is to benefit the community and the environment. By creating an efficient and sturdy bridge, not only will those who use the bridge have an improved quality of life, but everyone in the community will benefit from the construction. The engineers will have an easier time designing and building the project using multivariable calculus and the problem-solving steps that we learned in the class, and the people within the community can trust that the bridge is sound and sturdy without worry that the calculation went wrong since the process takes so many steps. This kind of works as a fail-safe to make sure that it is as secure as possible and that nothing will cause the foundation to fall or the bridge itself to be built in a way that is not appropriate for the space that it's in. Crash Course has a really good video on the physics of engineering and structures that I've attached here. I'll play that in just a moment in case you wanted to watch it here.
After years of hard work as a student of engineering, you've landed a role as an engineer in a big company. Congratulations! Your new job even gives you a fancy office in a skyscraper. It's a sweet deal, until one day a terrible storm hits the city. That doesn't bother you too much at first. A bit of wind doesn't seem like a big deal when you're in an office. But as you're working at your desk, you notice the entire skyscraper begins to sway in the wind. In fact, the building tilts so much, your pencil rolls right off your desk, and the view outside of your window starts to angle towards the sky. In 1978, the City Court building in Manhattan came dangerously close to that scenario. If a powerful enough storm had happened before anyone realized, key parts of the structure could have failed. And all because the engineers who designed it didn't account for how all the forces acting on the structure could affect its stability. But by considering those forces and how to counteract them, an industrious team of engineers managed to save the City Court building before any disasters happened. As you'll recall, is any interaction with an object that, if unopposed, would cause it to accelerate or change its momentum. Like, with the skyscraper, you don't want forces like the wind seriously deforming the structures you build, or even causing them to collapse entirely. So it's important to design things to be able to withstand the forces they may encounter. When the City Court Tower was first built, it had a slightly unusual structure to accommodate a church on the corner of the block it was built on. The whole building was raised on 9-story high stilts, but because of the church, the stilts needed to be in the middle of each side rather than in the corners, which meant quartering winds, which blow diagonally to the faces of a building rather than straight on, became a problem. Ordinarily, these winds aren't a huge issue since they blow past the structure without applying much force to it. Unfortunately, having those columns on the building's sides made it more vulnerable to quartering winds than the engineers originally thought. And they didn't notice until after the building had been built, when a student writing a paper on the City Court building realized there was a problem and brought it to the attention of the lead structural engineer. Essentially, Essentially, they'd made a critical mistake when they calculated the building's statics and dynamics. Both of these are branches of mechanics, a field that considers how forces affect a structure's behaviour. Statics, as the name implies, is about what happens to objects that don't accelerate when a force is applied. All the forces acting on the object balance out, keeping it rigid. It doesn't rotate or move from its original position. When this happens, we'd say the object is in static equilibrium with its environment. Dynamics, on the other hand, deals with what happens when the various forces don't cancel out. If the structure isn't held in place by friction or attached to its surroundings in some other way, a large enough force will cause it to move, rotate, or deform. That's when dynamics comes into play, and you'd have to consider the object's motion. The good news about that is that the same basic idea governs both statics and dynamics. Newton's second law of motion, which says that the force acting on an object is equal to its mass times its acceleration. But an object like a building or bridge is made of many connecting parts. If the mass is distributed throughout the structure, a force applied at one part of that structure won't affect the entire thing in the same way. It's also important to note that Newton's second law assumes the force acts in a given direction. So in reality, it's not quite as simple as F equals ma. Instead, you have to consider the direction the force is applied in, which also determines the direction of the acceleration. Quantities that have both magnitude and direction are called vectors, and you have to take the direction into account when you add them together. Both the F and A in Newton's second law are really vectors. To know the final motion or overall force acting on a structure, you need to add all the forces acting in different directions on each part of it. That might sound like a lot to consider, but there's a clever way to keep track of all of it. As we've mentioned in statics, we're looking at a situation where all the forces are balanced to zero, static equilibrium. These calculations are important for making sure your structure is never on the verge of failure. Objects can only handle a certain amount of stress before they deform or break. Statics helps you work out the force that parts of the structure are experiencing under a load. Since by definition, all the forces on the structure have to cancel out to zero, if you know some of the forces acting on it, you can usually figure out the others. To make sense of all of this, engineers use what's called a free body diagram, a sketch of the structure and all the known forces acting on it. Consider, for example, a bridge. The material the bridge is made of contributes to its weight. Rather than show the force of gravity acting on all the little bits of the bridge, you can average all the contributions of its mass and draw a single force on the diagram acting on what's called the centre of mass. Now, say there's a goat trying to cross the bridge, maybe to get to some greener grass on a hillside. Luckily for the goat, there's no troll blocking its way. Since the bridge is in equilibrium and both the goat's weight and the bridge's own weight are pulling it down, there must be some force counteracting this to stop the bridge from dropping into the river. In this case, you would use static equilibrium to calculate the force each of the supports have to apply to the bridge to hold it up. The details require a bit of math and careful thinking, but the basic idea is, if you add the contributions of all the forces in each direction, being careful to give opposing forces different signs in your equations, everything should balance out to zero. So at a glance, you already know that the sum of all the forces acting upward from the supports of the bridge has to cancel out the downward forces of the weights. The full treatment would require a bit more work, of course. If it was a suspension bridge, the weight of the bridge and the goat would be counteracted by the vertical component of the tension in the cables. If those cables can only handle a certain amount of tension before breaking, a free body diagram could help you work out the total weight the bridge could handle before the cables snap. It's also important to consider the torque. Any force that could cause a rotation of an object around a point is also sometimes called a moment. Torque is usually a factor when part of a structure is fixed to some point about which it's free to rotate, called a pivot. If you've ever been to a playground, you might have seen some torques in action on a seesaw. Let's say there are two twins with the same weight, Parvati and Padma. Both twins sit on a seesaw 1.5 metres away from the pivot. They both weigh 600 newtons, the equivalent of about 61 kilograms of mass, being pulled down by gravity. They're exerting torque because on their own, each twin would cause the seesaw to rotate. The torque comes from the force of the twins' weight pushing down on the seesaw, perpendicular to the line connecting the seat to the pivot. The heavier the twin, the more force they'll exert and the stronger the torque will be. Their distance from the pivot matters too. If Parvati moved closer, she'd exert less torque than Padma, and the seesaw would swing her upward. Those are the two ingredients you need for calculating torques: the force perpendicular to a line connecting to the pivot, and the distance from the force to to the pivot. Multiply those together and you get torque, which is measured in units of Newton meters since you're multiplying force by a distance. As with forces, in a static scenario, like the twins balanced on a seesaw, you can use the fact that everything balances out to zero to help you. If you add up the torques, defining either clockwise or counterclockwise as the positive torque direction, they'll equal zero. In this case, Parvati and Padma each create torques of 900 Newton meters in opposite directions, which cancel out. Of course, if Padma swaps places with a heavier friend of hers, the torques will no longer add up to zero. If the seesaw was long enough, she could balance out the torque generated by her heavier friend by sitting further away from the pivot. But if they're sitting the same distance away on opposite sides, we have a dynamics problem rather than statics. By adding up torques or forces, we could work out the total torque and Parvati's change in angular momentum, or the momentum of her rotation as she begins to swing upward. So dynamics describes when the net force or torques on the system don't cancel out. That was the problem for the City Court building. The force of the wind had a significant chance of overwhelming it. Big skyscrapers ordinarily resist the wind through a system of braces inside the building's structure. As we've seen for the other engineering materials, the braces can withstand a certain amount of stress before they begin to undergo failure. In the case of the City Court building, the students' discovery prompted the lead structural engineer to consider the quartering winds. He realized that the positioning of the building's support columns meant the total wind force on the braces would be way more than they planned for. By looking at how the force of weight was distributed throughout the building and calculating how quartering winds would distribute a force to the braces, he found that some of the braces would encounter a tension of 160% more than they previously calculated. It would only take a once in 16-year storm for the braces to fail. Thankfully, he and a team of engineers worked through the full mechanics of the situation and realized that they could reinforce the braces by welding 5cm thick steel plates throughout the structure. To get the job done without causing too much panic to the inhabitants of the building or alerting the media, welders worked at night and in secret to reinforce the braces. After a few months of welding, they transformed the City Court building from having a 1 in 16 chance of failure in any given year to one of the safest buildings ever built. Today, it can handle pretty much anything the weather throws at it. In this episode, we looked at statics and dynamics and what they mean for the structures we design. We explored the idea of static equilibrium, forces and torques, and how free body diagrams can help us make sense of it all. In our next episode, we switch from looking at the math engineers use to solve problems to the decisions they have to make to acknowledge and admit problems in the first place. Crash Course Engineering is produced in association with PBS Digital Studios. To learn more about physics in the real world, check out Physics Girl. Diana Karen demonstrates the physics behind puzzling phenomenon and everyday mysteries. Check out Physics Girl and subscribe at the link below. Crash Course is a Complexly production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.